Hello and welcome back to Atomic Math. Today we're going to take a look at what exactly causes astronauts to float in space, because it's not what you probably think. Most people assume that an astronaut is floating because there's no gravity, but let's think about that for a minute. We know the moon orbits the Earth because of the pull of the Earth's gravity. We also know that the moon's gravity affects the tides of the ocean here on Earth. We know that gravity can act over vast distances. The moon is almost 400,000 kilometers away. So, is it reasonable to assume that an astronaut who is only 400 kilometers from the surface of the Earth would not experience the pull of gravity? The answer is definitely no. It is not reasonable. The astronauts most definitely are feeling the effects of gravity. In fact, we can take a closer look and we can actually calculate exactly how much gravitational force an astronaut would feel at a distance of about 400 kilometers from the surface. Okay, so we can use the following equation. And so this equation is going to calculate the force of gravity on an object. So G is the gravitational constant, which is 6.67 times 10 to the minus 11 meters cubed per kilogram per second. M1 is the mass of the Earth, which is approximately 5.97 times 10 to the 24 kilograms. And M2 is going to be the mass of our astronaut. And R is the radius separating the astronaut from the center of the Earth. So not from the surface, from the center. So now let's take an actual look. First, let's look at what the force of gravity is for the astronaut on the surface. How much force does the astronaut feel when he's standing on the Earth? And we're going to assume for this that our astronaut has mass of 70 kilograms. Let's use our equation, and if we plug in our values, we're going to get this. You can see that down below on the bottom for R, I've used 6.38 times 10 to the 6 meters. That is the approximate radius of the Earth. So at the time when you're standing on the surface, that is the radius from the center. So on the surface, the astronaut is going to feel a force of 685 newtons. So we'll save that for later. Now let's look at what the force of gravity will be on the astronaut, who is 4.08 times 10 to the 5 meters above the surface, which is the approximate altitude that the space station orbits in. So as I said, the radius of the Earth is 6.38 times 10 to the 6 meters, and since the astronaut is 4.08 times 10 to the 5 meters above the Earth, our new radius is going to be adding those two numbers together. But everything else is going to stay the same, and we are going to find that we have 605 newtons. Now let's compare these two. So on the surface we feel 685, and in orbit 605. Well, that's not that much of a difference. In fact, if I take the ratio, I get 0.883. So this means that the astronaut is still feeling 88% of the gravity they experience on the surface of the Earth. This basically means if you weighed 70 kilograms on the surface, you're still going to weigh about 63 kilograms in orbit. And that is definitely too heavy to float. So why do we always see them floating? Well, that is where things get really interesting, and for some people a little bit scary. Astronauts are actually in what we call a free fall. And to understand this, we need to look at projectile motion. When you throw an object horizontally near the Earth's surface, it will quickly hit the ground as gravity pulls the object towards the Earth. This motion is called projectile motion. The object follows a parabolic path if gravity is the only force acting upon it. Now, let's look at this diagram here. We can see that we have two balls, an orange ball and a blue ball. The orange ball was thrown with a slower velocity than the blue ball, and they both will hit the ground at the same time, but the blue ball had more speed, so it was able to travel farther before it hit the ground. And this basically means that the faster the horizontal velocity, the larger the arc of the curve will be, because both balls experience the same downward pull. The only thing that's different is the horizontal component. So the faster we go, the larger the arc of the curve will be. And you can imagine if you kept throwing it harder and harder, making it faster and faster, eventually you would actually have an arc that is large enough to match the curvature of the Earth. So this is why astronauts appear as they're floating. They're actually falling around the Earth. So why do astronauts feel like they're floating? Can't they feel that they're falling? Well, in some ways they can, especially at the very beginning. But the thing is is that our bodies can't actually detect motion without the help of things like sight. What we can feel is acceleration. And Newton's first law, a body at rest remains at rest, or a body in motion remains in motion in a straight line unless it is acted upon by a force. So if the astronauts were not accelerating, that would explain why they are not feeling like they're falling. However, that is not the case. The astronauts are accelerating. So that idea won't help us figure out why they don't feel like they're falling. For that, we need to really understand what's happening with acceleration. So I want you to imagine that you are trapped inside a windowless box and consider the following two situations. The first situation, you're trapped inside a box, you're here on Earth, everything feels normal. Well, you are trapped in a box, but physics-wise, everything feels normal. You feel your body weight on the bottom of the box. The second situation, you are in the same box, but now you're in space in the absence of gravity, but the box is accelerating at a rate of 9.81 meters per second squared, which is equivalent to what you feel on Earth from gravity. So when you're in this box, as far as you're concerned, the side of that box, the left side of that box, will feel like it is the bottom of the box and you are here on Earth. You would not be able to tell the difference between you in space and you on Earth because you cannot see outside the box. So on the Earth, your body is feeling the normal force of the bottom of the box pushing back up against you. And in space, your body is feeling the normal force of the left side of that box, which is pushing up against you. So you can see how in both these situations, whether you're in a gravitational field or not in a gravitational field, acceleration can actually make you feel like you're in a gravitational field. Again, that doesn't really explain our astronauts, but I want to compare the two situations. So this was our first situation of how this would feel to you in a box. The second situation, I want you to imagine that you are trapped inside the same windowless box, but this time we're going to change the situation. This time you are an astronaut. So you've got your spacesuit on, you're trapped inside this box, and you're just casually floating in space. Everything feels normal to you, physics-wise, because you believe you're in space and you are floating, and you don't feel any gravity. So you think everything is normal. Now, imagine the second situation that you're actually not in space. You're here on Earth, well, above the Earth, and let's say someone threw you out of a plane in this box, and you're now free falling to Earth. And for this thought experiment, we're going to pretend that you were unconscious at the moment that they threw you out of the plane, and you only became aware of your surroundings once it was already accelerating. And the reason for that is because when we fall, what we actually feel is that jerk. We feel the sort of quick change in acceleration. And if you take that away and you're just in a constant acceleration, that removes that sort of strong jerking feeling. So in these two situations, you would not be able to tell the difference. If you were the green astronaut thinking that you're happily floating in space, when in fact you're actually plummeting towards the surface of the Earth, your happiness is going to be short-lived. But you would not be able to tell the difference. The green astronaut and the blue astronaut would think that they're experiencing the exact same thing. So why is this? Why can you have these two situations? Both cases, the boxes were in a gravitational field here on Earth versus a non-gravitational field in the sort of vastness of space, but we're getting different results from the first comparison and this comparison. So to understand what that difference is, let's compare our free falling on Earth to our space accelerating. So now I'm mixing them. The difference here is, and the reason why we feel acceleration. So if you imagine you're in a car and it's accelerating quickly, you feel that push. You feel that push on your back. And that's what we're feeling when we feel acceleration, is that push. So we only feel acceleration if there's a surface pressing against us. So for example, in space, this box is sort of traveling horizontally at the same acceleration as gravity is here on Earth. They themselves are not actually accelerating. It is the box that's accelerating. And they were going to remain in one place, but because the box is solid, it will push you along with it. And so that is why you feel the acceleration, because it wasn't your body that was accelerating. The box was accelerating and it's pushing you with it. Now, the situation on Earth is different. Gravity is acting on both the person and the box equally. So in space, the box alone was accelerating and it was pushing on you. Just like when you're in a car, the car accelerates and it brings you along with it. But gravity is a force that can act on everything without actually touching it. So the person in free fall is experiencing acceleration due to gravity, but there's no surface pushing on them. So that's why a free fall due to gravity feels exactly the same as floating in space. The astronauts are basically in free fall, and this is why they're not really feeling that obvious sort of sense of falling. However, they do sometimes feel a little bit of a falling sensation, but when they go up into orbit, they get into orbit gradually, so it's not like they step off of a plane and just start dropping. They're gradually getting into that fall, so it kind of helps acclimate the body. So if you like this video, go ahead and hit like, and if you want to see more videos like this, hit subscribe, and I will see you in the next video.